Welcome to the course. Today, after seeing consensus, we're going to see another important thing that makes the internet take over the world, which is called shared memory. Shared memory, okay, shared memory, it's memory like you see in a regular computer architecture. So you have an address space, you have blocks of memory, addresses that you can store and read and store. So we don't assume message passing. Okay, so the distributed system, of course, it sends messages, but here we want to make an illusion that the whole system is like one memory. Okay, all nodes access one shared memory. Many machines are like that. Multi-core, multi-processors, most machines are like that. Okay, here I have 4 cores and they're all accessing the same memory. So this is what we want to do. We want to do shared memory using, of course, it will use message passing because the distributed system will send messages. Okay, so we want to simulate shared memory using message passing. Simulate that the distributed system has a shared memory. Each memory location, we will call it a register, like in the processor, but so just to make the terminology simple, we'll have registers. So each node can read and write 2 registers. In a regular architecture, that's just a regular read and write instruction, okay? So we want to simulate that. See, we want to simulate that. So why is that important? If you look at it like that, big deal, right? Well, you can think of registers as objects. There's also code there. It's like the attributes of objects. Registers are like, they store the data, they're objects. We will give you simple algorithms just using registers, but in your imagination, you have to think that this is just the heart of it, of a big thing. So there's objects. And more than that, it can be many kinds of, so nodes can read and write, but we can have many kinds of data structures, FIFO-Q implemented. And in fact, it all leads to databases. A simple database is called a key value store, where it's kind of like a hash table. It's what's called NoSQL, where you have keys which are just constants identifying the registers and you can store and read them. But all databases are built on top of that. Databases with transactions. Underneath, there's a key value store. And then you have code doing the transaction. Okay? Distributed databases. The basic kind is what's called NoSQL. SQL is standard query language, is a query language which is used a lot for big databases, but it's very complex. So there was a movement to make simplified version called NoSQL, and that's just a key value store. But even regular SQL databases have registers. Okay? So what I'm going to tell you today is underneath everything on the web. If you use Amazon or Google, you're using consensus, but you're also using shared memory. Because Amazon, where does it store all the stuff that you do? Your accounts and the money and everything and the stock. It's stored in a database. What's called Web 2.0. Web 2.0 is where you have automatically generated web pages. They're not all stored statically. So when you're using Amazon or whatever, it's all Web 2.0. Okay? And behind what you see is a database. Today, I want to show you the algorithms that do that. Okay? Okay? So why shared memory? Well, in fact, you can call it consistent replication. Technically, you have the same register stored on many nodes, and when you write, you have to update them. But what if you have concurrent writes? it still has to update consistently. What if one node is written and the other node reads? Well, you have to read what you write normally, right? But that's not so easy, because what if you write here and you read somewhere else? Underneath you have to have something. And that's what's called consistent replication. And we also call it a single system illusion. So the abstraction is called an illusion, okay? And it's replicated because, for the usual reason in the distributed system, because we want fault tolerance. In a distributed database, if one of the nodes fails, the bank should keep working, Amazon should keep working, huh? Otherwise, Bezos will lose many billions. So of course it's a distributed database, huh? And it's also scalable because they want as many users as possible, millions. And when Christmas arrives, the number of users explodes. So that all has to be handled, okay? So it's replicated, it's concurrent, of course, it's fault tolerant, scalable, and it behaves like it's a single memory. You do write and you read what you have written, and you can do it concurrently and everything. So that's the idea, and that's not so simple to do, okay? So we want consistency. So consistency means that when you write something and then you read, that you read what you have written. Okay, so that's the intuition. We can make precise definitions of it, which we will do. And you can have failures and you can have concurrency, the usual distributed system. We want to increase the reliability. So a system that's built like this can be extremely reliable, even if the components are failing all the time. You don't notice it. Well, when you notice it, it's newspaper something, huh? Facebook has a 3-hour outage. Ooh, it's in the newspapers. But it's actually pretty rare that that happens, huh? Amazon is very rarely out, huh? So that's because of this. Because that they did it right, this implementation, okay? So that's the idea for shared memory. So you can see it's an important thing. So you can see we have some real important kinds of algorithms. We have the broadcast, which is communication, like causal broadcast. We have the consensus, which is like agreeing. And now we have the shared memory, which is even another important thing. You can see that there's different kinds of important things, huh? Okay, so let me make a definition now of a read-write register. And today I'm going to talk about algorithms for implementing this. Okay, so how does it look like? Well, when you read, okay, you have register R and you have read and write. So when you read R, it returns some value, X. And when you write R, you write a new value, X, into R. So these are the two operations. And in fact, because we're a distributed system, we cannot assume these are instantaneous. The read and the write, they start. You start it, which is called the invocation, and then eventually it's done. And that's the response. So the write here, you start it here, and here you get a message saying it's done. The write is finished. And here you have the read starts, and here you have actually the value being returned. So both the read and the write are not instantaneous things. In a single machine, like this machine, you can kind of consider them instantaneous. They're single instructions because it's so fast. It's like a nanosecond or something. But in a distributed system, you cannot do that because maybe you have to go on the network and this might take some time. So you have to make the difference between invocation and response, okay? So that's how we're going to specify it. So today I'm going to give you lots of algorithms for this simple thing. And here is register R, but usually I'm going to have only one register. And so I won't even give the name of the register R. The R is the name of the register. I'll just have a read and write. And then you can imagine that there's millions of those, and that there are objects and databases and whatever. But I'm just going to give you read and write of one register, okay? That's the basic idea. And a few more simplifying assumptions. These will not, it's still completely general. I'm assuming the nodes are sequential, so each node will do only sequential operations. It will do an invocation and a response. So it might do a read and then a write, and then a read and then a read, and so on. It only does one operation at a time. So this does not reduce generality, because of course you can have as many nodes as you want, and the nodes are going to be concurrent. But each node by itself will be sequential. That's simple in the algorithm. And the values in the registers, of course, they can be anything. They can be huge data structures, but I'm only going to use positive integers, numbers, natural numbers, and initially 0. So that's all simplifying, but it doesn't reduce generality. So this is really getting to the heart of things. Okay? Now, we have to be very precise also because of failures. We say an operation, so a read or write, is complete if you do both the invocation and the response. So the whole thing is done, it's complete. But maybe there's a failure. So you can have invoke, started, but it never stops. No response ever arrives. So that's a failed operation. Of course you can have failed operations, Okay? You can also have an order. So this is an ordering that you can use to define also a causality. So one operation precedes another one. That's very intuitive. The response of this one is before the invocation of the second one. So if this one does a write, then the response, that means the write is finished, and the read will start after. That means they're not overlapping, they're separate. Okay? So that's a causal. There's an order. You can use it to find a causality. But that's important because usually when you read what's written. Okay? And you can see that here we're looking at the end of op1 and the beginning of op2. Because you have a response, invocation, response in both cases. They're like intervals, so they don't overlap. Of course, they can overlap. This is why it's interesting, right? Distributed systems. This is the easy case, Well, what if they overlap? Well, we say they're concurrent. And things become weird when they overlap, okay? And this is when it starts getting interesting, of course, This is when people get headaches and it starts getting hard. When they can overlap, okay? So that's terminology. Complete, failed operations, the ordering, precedence, and concurrent. So this concurrent is super important, of course, because it's going to happen a lot in distributed systems, You see, The usual thing. It's hard, okay? That's not changing. And we're going to see two kinds of algorithms. This is a kind of standard terminology. There are 1n algorithms and nn algorithms. So this kind of tuple, the first number is the number of writers, the number of nodes that are allowed to write, and the second one is the number of nodes that are allowed to read. So the most general one, the one that does the most general thing, of course, is nn, where anybody can write and anybody can read. Okay, multiple writers, multiple readers. But that's hard, okay? That's hard. So we're going to start with 1n, where only one node can write, but many nodes can read. So the writing node will be kind of broadcasting the value. And you still have to worry about consistency here, because the messages, we don't know how long they take, and you can have failures and stuff. So we'll start with 1n algorithm, and then we go to nn algorithm. Okay, step by step. Okay, so let me give a kind of a roadmap of how we're going to do it. So that, first of all, the kind of register, this is how strong the consistency is. So we're going to start with a very simple one called a regular register. And then we're going to go to more complicated ones, which is called sequentially consistent register or linearizable register. The linearizable one is also called atomic. So those are also kinds of registers. So this is the level of consistency, okay? This is how strong it is, how close it comes to the regular memory on your laptop. So the linearizable is the one. This one is exactly like a machine here. It behaves exactly when you do write and then you do read, you instantaneously see the write that does the write, and the read you will see the result of the write that happened before for the whole distributed system. So this is kind of the holy grail, the linearizable one, but it's hard to implement, you can imagine, and it's maybe slower. So we start with a very weak one called the regular register. But the advantage is that it's easy to implement, as usual. And then in the middle, there's something called the sequentially consistent register. These are sometimes good also. But it's also sequentially consistent is not much worse than linearizable. And both of these are pretty hard, actually. Okay? But let's start with regular register. And then on the other side, of course, we'll go from 1n to nn. And then we will also have fail stop and fail silent. Okay, fail stop, wow. Fail stop is our friend P, which makes it easy. And fail silent means we have no failure detector. So this one, fail silent, will work on the internet. So we're not going to do an eventually P, but we will show you a fail silent algorithm, which of course will work on the internet because you're not assuming any failure detector at all. Okay. So these are the kind of steps we will make. So as you go down, it gets more complicated, okay, and slower, but it's more powerful. So when you use a database like Cassandra or one of these cloud databases, then they will be usually giving you choices. You can usually tweak them and tell them what level you want. And the more you want, the slower it'll get, okay? You have to pay, of course, You have to pay if you want something. Okay. Let me now start with regular register. You'll see it's actually not too bad. So this is a 1n regular register, okay? Okay, so there's, of course, properties, as usual. Termination property. Each read and write operation of a correct node completes. That's reasonable. The node is correct. It completes, doesn't fail. And validity, so this is the interesting one. Okay, the read, what we want is that the read returns the last thing you write, of course. That's what you want. But you don't always get that. Okay? You get it sometimes. The read returns the last value written if it's not concurrent with the write. So if there's a read and a write that are overlapping, like this, then we're not sure. Then we might not get this value. But if the read and the write are sequential, like this, then we will get the last value. Or it's not concurrent with a failed operation. Yeah, failed operations, they mess things up, of course. So the read, so in this case, if there's no overlap, so the no overlap case, the read has to return the last value written. That's reasonable. So if I write 5, then I have to return 5 here. So if there's no overlap. But if there is an overlap, there's also a condition. It either returns the last value written or a concurrent value. So if I have a read here, for example, and I do write of 5 here, and here I have a write of 6, notice there's an overlap here. This read is allowed to return 5 or 6. We can't be sure which one, but it has to be 5 or 6. So you can see what messes it up is the concurrent operations. Huh? But still, the read cannot do something random. It has to return either the last value written or a concurrent value that's still being written. Huh? So during this interval, of course, things are happening. Huh? And there's some overlap. So who knows what happens during this overlap? Huh? So in this regular register, it has to return one or the other. Okay, so here is an example. Here's a time-space diagram, P1, P2, P3. The register has 0 in the beginning. Here I do write of 5. This read returns 0. This read returns 5. This read returns 0. This read returns 5. And this read returns 5. That's weird, huh? So here I'm reading 5, I return 5. I read again, and then I get the old value. That's kind of weird, but maybe it's okay, who knows? And here I read again, and I get the new value again. And here I get the new value. So you have some weirdness here, huh? So is this a regular register? Now you have to tell me. Is this regular? Is this correct? Why?
Because the read and the write, which is not correct, are concurrent. So
which one?
The 0 and the 5.
This one and this one are concurrent. Yeah.
So it may read older value. Which
right. That means it's allowed to return 0, which is the previous value, or 5. And it's returning 0, so that's okay. This one returns 5. This is again concurrent. Huh? So this one also is allowed to return 0 or 5. And this one, what about this one?
Has to return 5.
This one has to return 5 because it's after the end of the write. And this one? But these two are concurrent.
But not read.
But they're both reads. Okay. Okay. Yeah. Okay. Okay. So this seems to be fine, right? This is allowed. So you see, regular registers can have some weirdness, huh? When there's concurrency. So in real systems, to make this work well, you try to reduce, of course, this. You try not to. You don't really want this weirdness, huh? But the algorithm is pretty simple for regular registers. Okay. I will now give you an algorithm. First, I give you a very, very simple. So as usual, we start with very simple algorithms, and we build up as we go farther. So here's a very simple algorithm. One process is the leader. This is a 1n algorithm. And this is the read code and the write code. So this is really high-level pseudocode. If I want to read, I ask the reader for the latest value. So basically, I send a message to the reader and I ask what is the value. And to write, I send a new value to the reader. Okay? So in this algorithm, this centralized algorithm, I have one process only, storing the value. And in order to read the value, I send a message asking for it. And in order to write, I send a message asking to update. So it's a little bit like client-server. The leader is kind of like the server of the register, and all the other nodes are like clients asking to read and write. Okay? So that's an algorithm, huh? Very simple one, right? Seems to be correct. Of course, this algorithm has a kind of problem, huh? Even though it's correct. You can imagine what the problem is, huh? What kind of problem would this algorithm have? I mean, it's correct, but I mean, as distributed systems people, you have to, this kind of algorithm. The first word in the title will kind of already hint it, yeah?
We're in the distributed system class and we'll see only centralized algorithm.
Yeah, but what's the problem with that? Maybe it's okay.
Oh no, the leader can just fail.
Exactly. When the leader crashes, the whole thing doesn't work anymore, okay? Boom. So this algorithm is not good enough for us, huh? Of course, you can always do it like this, but this is really not good. So let's try to make a better one, which is not centralized. Okay. Okay, let me do it in 2 steps. The first one, I call it bogus because there's going to be a bug in there. Yeah?
Wouldn't it be possible with leader action?
Yes, yes, of course, you can do, but you have to be very careful. Leader election, if the leader fails,
Yes.
what happens to the value? The value disappears if it's only on one node, right?
Yes.
So when the leader fails, the register, poof, the value just disappears. That's not very good, huh?
Yes.
So we don't want the values to just randomly disappear. Huh? But yeah, but you could. But the algorithm will be kind of going in that direction. Huh? It'll be a little bit like that, but we'll see. But of course, this is a whole, these kind of algorithms, it's a whole area of distributed systems. If you look at the book, there's like even maybe a chapter on only shared memory, okay? So these are kind of special kinds of algorithms, and there's lots of tricks and things. So today you're going to see only an introduction, but you will have the most important ideas. So once if you understand everything I say today, you'll be able to read lots of stuff, even more sophisticated algorithms, okay? So here let me present another algorithm. So the intuition is now that everybody gets the value. The write will write to all the nodes. So it broadcasts the value everywhere, and the read just has to read the local value because it's there. Okay? So that means the value is replicated on all the nodes. Okay? So here's an algorithm. So the write is, I update the local value to V, I broadcast, so I send a message to all nodes, and when the node receives the message, it locally updates, and I return. And the read is just returning the local value. Okay? So that's a better algorithm, right? Of course, this algorithm, as it stands, is still buggy. Okay? It's still buggy. But it's almost correct. If we do it like this, this broadcast could be like best effort broadcast or something, huh? So this algorithm can sometimes have a problem, okay? And maybe I show you a scenario of this. So here's a scenario. I have two processes. This one does write 5. So the write will send a message to P1, huh? And P1 is doing reads, but this message might be very slow. And then it does a read here. So what do you think? So this behavior is in agreement with this algorithm, huh? Because these broadcasts is just a send, huh? I'm not waiting for any return, huh? I'm just sending like best effort broadcast, huh? And this is the scenario. So is this okay?
No.
Yeah?
We do not decide when the write is finished, right? Because we don't know when it has been received.
Yeah, so here you send all of it and then immediately you finish the write. But in fact, it's not really finished yet. Yeah, and that's the point here, huh? Because the messages are still in the network. So the problem is when you do a read and it overlaps with a write, then you're allowed to return the old value or the new value. Okay? But this point is not actually the point where it's really done, which satisfies this condition. Huh? So you have to change a little bit the algorithm. And this gives us our first correct algorithm. And this is what I call the read one, write all, one n algorithm using perfect failure detector. Okay? So the write will do as before, but it has to do a little bit more. What does it have to do? Wait for acknowledgements, huh? It can only stop when it knows that all of the correct nodes have received, okay? It waits for acknowledgement from all correct nodes. This is why we need a perfect failure detector, huh? Because if the node failed, you can wait forever and nothing's gonna come, huh? So this will make sure that the wait actually terminates, huh? And once you do, you get that, you return. With this, the write will actually wait long enough, and then you will not have a problem anymore. Huh? So writing it, it's like this. Huh? So here's the original scenario where you just do a send, and then the write is done when the sends are done. But this is wrong, because when the sends arrive, that's when the register updated. So the write is actually only finished here. So the second one, it actually makes the write longer, so it only finishes when it gets the acknowledgements. And here, if you have reads happening concurrently, then it depends on how fast this message is, huh? If the message is very fast, the reads will return 5. Here the message is very slow and the reads return 0. But it's always going to be 0 or 5, huh? And when it's actually done, then we know it will always return 5. So this one will satisfy regular register, huh? So during the write, concurrent with the write, depending on how fast the messages are, we can either get the old or the new value. Huh? And after the write is done, we're sure to get the new value. So that's perfect. That's perfect for regular register. Huh? Okay? So that's nice, right? So that is a fail-stop 1N algorithm, huh? For regular registers. Fail-stop means we have a P there. Of course, P is hard to do, but sometimes you have it, and then you can do that. And it's 1N because we only have one node that's actually doing writes. The others are only doing reads. So you think, oh, that's kind of annoying. But actually, sometimes it's reasonable. Assume I have a distributed game with a huge game space and players playing concurrently. And the game space is distributed over many servers. Each player has its own state. And so the player is like a register. And the player will be moving around, and so it will be doing writes. But since the player is localized on one node, it's exactly this. The other nodes are only going to see the faraway game state, so they will only receive messages, you see? So even the 1N can be useful. You don't always need to do updates everywhere. So the 1N is actually used a lot, okay? You see that? You see the case? I know that many of you are gamers, right? So you will understand the intuition that 1N is actually useful. Although NN, of course, is the most powerful one. You always want power, but you don't always need it, okay? But still, we have this problem of the P here. This one will not really run on internet. So I want to give you an internet version for a regular register. And the best way, the simplest way to do that is to give you a fail silent. So fail and silent means it does not use failure detector at all. It uses another technique. We actually saw already some kind of fail silent. There's another approach for fail silent. Remember what approach we used? I don't know if you remember, but you will remember it, because now I will explain. So fail silent now, we have this notion of majorities and intersections. Okay? Now in fail silent, nodes are allowed to fail, but we don't know which ones. But there's a limit on the number that can fail. Like maybe less than half or something. But we don't know which ones, and there's no failure detector. So we use this principle called quorum principle. This generalizes what we saw before. Remember, if you have two majorities in a set of nodes, two sets which each have more than half of the number of elements, then they must have a non-empty intersection. It's clear, huh? So the idea is very simple. You will always write to a majority, and you will read from a majority. And if you do that, you will always, the read will always have, there will always be one node which has seen the most recent write, because there's a non-empty intersection. You see the trick? It's nice, huh? So here's a write. So here we have 9 nodes, and the majority is 5, huh? So half of 9 is 4.5. So it has to be greater than half. If the number of nodes is odd, then it's here, it's 5. If the number of nodes is even, it has to be one more. Huh? If you have 12 nodes, you need 7, of course. Huh? But here for 9, you have 5. So the write will write to 5 nodes, and the read reads from 5 nodes, any 5 nodes. Of course, you can have failures in here, but you will always, if you write, the idea is the following. You write to everybody, and you wait to get acknowledgments from a majority, and then you're done. Here, you read is you ask for the value from everybody, and when you get returns, you only wait for a majority of returns, and you're done. So if nodes fail, you don't care if they're limited. And so you will guaranteed, the read will have seen the most recent value. You see that? And the write will use sequence numbers. So the idea is when you do more than one write, you can always tell which is the most recent one. You count them. So the read will look at all these nodes, and it will pick the most recently written value. And you're guaranteed it'll be the most recent write. Yes?
If the intersection crashes.
If the intersection crashes, there will always be an intersection that doesn't crash. If the intersection crashes, yeah, then you will have nothing, of course. But then you have too many failures. If you have less than the majority of failures, then there must exist an intersection that will not crash. Here, let's say you have 4 failures, okay? There's only 5 correct nodes. Well, you will write, and you will get acknowledgement from 5, and you will read, and you will get acknowledgement 5. Even in that case, they will completely overlap, okay? You see? So this cannot be empty, because if this is empty, then you have too many failures, in fact. Okay? But it's a very good question. You know, you point your finger exactly to the hard bit, huh? You see why that cannot be empty? Yeah, another question?
We have to know the majority, how much is the majority. So
oh yeah, you have to know how much it is, of course.
Which requires us to have...
Oh yeah, absolutely. You must in advance know what the majority is. So for this kind of system is actually used in databases. So let's say I have a database like Cassandra in a cloud, and you can configure it. Let's say it has 5 copies. And you know that when you set up the database. So the majority will be 3. You know that. And when you do reads and writes, automatically the system will wait for 3 things. But because you know it's a small, fixed number of nodes. If you have huge thing like peer-to-peer network with millions of nodes, you cannot use this kind of approach. Huh? You can use it for a small system where you know how many nodes there are. But that's still very useful. If you have a distributed database, usually you assume the nodes, they crash independently of each other. So one of them crashes because, I don't know, one of the integrated circuits burns out or something. It's random. But the other 2 keep running. So Cassandra with 5 nodes is extremely reliable, okay? Because the crashes will be kind of independent. So making a system with a small number, a fixed small number of nodes, will increase the reliability by a lot. So it's still very useful, okay? Of course, you cannot do everything. Like you say, you cannot, if you don't know how many nodes, then you cannot use this approach, okay? You see that? You see how it works, huh? This is a crucial idea in distributed systems. And this works also when you have failures, of course, huh? So here you're assuming the number of failed nodes is less than half. So I can either have 0 failed, 1, 2, 3, or 4 failed nodes. In all of those cases, the intersection will be non-empty, okay? You see how it works, huh? The read will send messages to all nodes, and it will wait for a majority. And that is guaranteed to happen if the number of failures is less than half, huh? Okay? So you have to understand why this works Also in the failure case, this picture is not a failure case, but in cases where any number of failures up to half, so for 9 you can have up to 4 failures and it still works. Okay, so you see how it works, Yeah, that one. Now it's actually, let's generalize this. Majority is a principle where you have what's called quorums. You have, if you write to a certain nodes and you read from certain nodes, then you guarantee there's non-empty intersection. That works for majorities, okay? But there's other ways to do that. You can actually tweak that and get very interesting results. What we saw before is called majority quorum. And in a majority quorum, you will read, you will write to a majority and read from a majority. And this is the property it has. It will tolerate a certain number of crashes, but there's also an overhead. So the good part, is it can handle lots of crashes. So for 9 nodes, it's the ceiling of 9 over 2. So this is 5 minus 1. 4 nodes will tolerate crashes. But the bad part, is it has to do work. It has to read and write 5 nodes. You cannot read by just reading 1 node. If you want it to work, you have to read 5 nodes here. But if you do that, you can tolerate 4 crashes. But you can vary that. And let me give you another example, just to show you. But there's many, many ways to vary it. Here's another quorum approach. And this is called Maikawa quorum, because there's this guy who invented it. Okay? This quorum, you arrange the nodes in a square. Okay? So here you have 3 by 3, so 9 nodes. So if you have n nodes, m will be the side of the grid here. You're assuming it's a perfect square. And you will write to rows and read from columns. Okay? So you will keep writing. Basically, you write to everybody, and then you read, then you wait for acknowledgments that you have written to a row, like this one, 4, 5, 6. And the same for the read. You will ask everybody for a value, and then it will return, you will wait for things to come back until you have gotten at least 1 column. And you know that a row and a column must intersect, for sure. So that means if you do that, you are guaranteed to, just like here, you're guaranteed to always read the most recent value. So this one works too. This has a different, trade-off. The positive thing is, in fact, you only have to read or write square root of n nodes. You only have to wait for square root of n acknowledgements. So if n is equal to 9, that's only 3. You only have to wait for 3 acknowledgements. But it will tolerate less crashes. It will only tolerate square root of n minus 1. So it will only tolerate 2 crashes. Okay? So it's more efficient, but it's less fault tolerant. So you see the trade-off is different, And you can make other quorums. In fact, there's many, many ways of doing quorums. You can make a cube, for example. That gives another kind of quorum, where you can write in a square, like a slab, and read in a pillar, in a bar. And they will always intersect. That means the write will be n to the power 2/3, and the reads will only mean n to the power 1/3, for example. See, there's lots of ways, and you can invent all kinds of quorums. So they all have different trade-offs. So maybe your system is very reliable, okay? And it's very reliable, so you don't really need to wait be fault tolerant for 4 crashes. 2 is enough, because by far you will not get 4 crashes. You might get 1 very rarely, but almost never 2. And then if you do Maikawa, it's more efficient, okay? Because instead of writing to 5, you only have to write 3, so it's almost twice as fast. on average, huh? You have less work to do. It depends on the network, of course, huh? There's lots of variables here, and how the messages and so on. But you will have less messages to wait for. So in general, it'll be faster, but less fault tolerant. You see? So that's a way, that gives you regular registers at work on internet. See how it works, huh? So I'm going to give you some code for that now. So this is the majority voting algorithm. It's a 1N algorithm. And it assumes a majority of correct processes. You can, of course, generalize this for any quorum, huh? To make it work for any quorum. All the writes will have a sequence number. So the writes will be first, second, third, fourth, fifth write, and so on, and there's no failure detector. Okay? So here is the write. So you broadcast the value and the new sequence number to everybody. The receiver will update the value. Okay? And then you wait for acknowledgement from a majority. See how it works? So you broadcast to everybody, but you only wait for a majority. Then you increment the sequence number. Okay, this is C plus C notation. And you return. So that's the write. And the read is like this. Okay? Again, you broadcast a read request to everybody. Each receiver returns a pair of the local value and the sequence number. You wait and you get the values. But you only have to wait till you get a number of messages equal to majority. Any other messages, you just ignore them. You only need to wait for a majority. So if you have 9 nodes, you will send to 9, but you will only wait for 5 return messages. You see that, huh? And that's reasonable, because if 4 nodes fail, it still works, right? And then you return the value with the highest sequence number, and that's it. Okay. So you see that algorithm? You see that? So this one gives you an algorithm that works on internet and is 1N. Yes?
So we always have to store messages, because until we may...
yeah, you have to wait. Yeah.
At any time we may receive a message that was already received.
Okay. You're getting ahead of me. Yes. Yes, you have, I think you've smelled something. There's actually a small bug in this algorithm. And it's similar to the orphan messages we had. So here's a scenario, but the fix is very easy. Here's a scenario. I write 2. Now here I return 1, I return 2. So the majority is 2. For 3 nodes, the majority is 2. So I wait for 2 returns. And then I write 5. Again, I wait for 2 returns. But then here, okay, I will send the write here, and it's a slow message, okay? And the read, it's very weird. The read will return 2. And why will it return 2? Well, because notice that this one has a 2, but this one has a 2 also. Because this majority doesn't actually cover this one. It's this old message is killing us, huh? This old message can take this one node, which is not a majority. Yeah? There's still 2 here. Notice the write 5 does not actually go to itself. There's still a 2 here. But from this old message, it can turn into a majority again. So we're screwed in a sense, and we return 2, and that's incorrect. So we need to do a small fix, and it's a similar fix to the orphan. So old messages, somehow we have to get rid of them. So the fix would be something like this. When I receive a V, I only update if it's a newer value, okay? That's logical, huh? I don't update if it's an older sequence number that somehow survived and comes in, huh? So I need to do this condition. Otherwise it's buggy, huh? You see that? I think that covers your question, does it? Sort of, okay. Now the algorithm is correct, huh? So this is kind of like an orphan. You have to be careful when you have majorities, because the messages that are not part of the majority, maybe they're still traveling in the network. So you have to make sure they will not upset anything. Huh? Here you broadcast to everybody, but you wait for a majority. But everybody, that there might be still some messages kind of traveling. So you have to make sure they will not upset anything. So that means you might have to add some conditions to make sure that older messages don't upset anything, but you can tell when they're older because of the sequence number, right? So this algorithm is correct, huh? Okay? So this is a majority voting algorithm. So this is a 1N regular register that fail silent algorithm that works on the internet. And actually, some systems use algorithms similar to this, huh? Sometimes they don't need more than that. Okay? See that? It's nice, huh? Isn't it? Simple, huh? Well, it's simple because we're still regular, right? So I'm now going to do a break. After the break, we're going to do what they say, huh? In French they say, on va passer à la vitesse supérieure. Huh? We increase the speed and we go to linearizable. And it's a little bit harder. But this is actually very reasonable, huh? Okay? Let me make a break now, and then after the break we'll talk about your new linearizable registers. So now we go to the next level. Single storage is illusion. Now we want to make our system, our register, look exactly like it was a single machine. That means you do a write and you do a read, and instantaneously the read sees the result of the write everywhere. Okay, you can say, how can we do that? But we can do it, and you'll see how. There's two levels of this, okay? And these are safety requirements, huh? These requirements that it behaves like a single machine, that's a safety. That means it does not behave incorrectly with respect to a single machine. There's also liveness requirement, which I'll talk about after. But the safety requirement is the one that gives you the single storage illusion. Okay? And there's two levels of it. The first level is called sequential consistency. This is the standard terminology, yeah? And the second level, the strongest one, is called, it has two names, which are synonyms, linearizability or atomicity. So those two are used kind of, some people say linearizable, some people say atomic, okay? Sequential consistency, so let me say linearizable first. Would only allow executions whose roles appear as if there is a single system image and there is a global time that's obeyed. That means if I do a write on one node and I do a read on another node, it behaves as if the write was instantaneous and the read is instantaneous. And if the read is after, the instantaneous read is after the instantaneous write, it sees the written value, otherwise it doesn't. That's linearizable. Okay? Of course, the real system will not be actually instantaneous. Huh? So you'll see what it means. This little words as if is very important. Huh? It's in real life, it's not actually instantaneous, but it behaves exactly as if, and I'll show you what that means. And sequential is a little bit weaker. It's instantaneous, but on every node separately. That means if I do a write and a read on one node, it's exactly in the right, they're like instantaneous. But in between two nodes, I can have some kind of a delay. So this is only local time, whereas linearizable is global. So let me show you some scenarios here to show you how it works, also to compare it with regular. Here we have 3 nodes, and here I'm doing a regular execution, okay? Here I do a write 5, and on P2 I do read 5 and read 0. Of course, this is correct for regular, okay? But it's not correct for sequential, because in a sequential machine, if I read a 5 on P2, and I do another read after that, I will never read the earlier value. Clearly, there's a single local time here, okay? And once the register has 5, there will only be more writes, never fewer. So this is not allowed in sequential, okay? Consistency, and in linearizability neither, but here sequential because I'm only looking at the sequence of time on one node, okay? But it is allowed for regular. You see that? You see that sequential is a lot stronger here, because here it has to behave really this. I have an instant right here. Here I read 5, and here I must read 5, or a later value that's written. But here I don't have any later values, so I must read the 5 here. So this is not allowed in sequential, but it is allowed in regular. Okay? Happen before observable on the same node, and sequential does not allow that. Okay? Okay, again, it's the same for linearizability. Linearizability is stronger because it looks at all of the nodes, and not just P2. But here, it's enough to look at P2. If we had more, if this operation would have been here, then it would have been okay for sequential, but not okay for linearizable, okay? So linearizable is strictly stronger than all linearizable systems are also sequential, yeah? Okay? Okay? Now here's another one. Notice I have again write 5. I read 0 on P2, and I read 5 on P3. Notice this read 5 happens before this. It's before in time, in absolute time. But these are on different nodes. So sequential consistency actually allows this, because the time, each node has its own local time, and there's no connection between them. So there's no connection between these two in sequential consistency. If I were to do another read here on P3, it has to read 5, of course. Even if this one reads 0, this one would have to read 5 for sequential consistency. But sequential consistency doesn't make any connection between nodes. But each node by itself is perfectly ordered, like it was a single machine. Okay? So this is actually allowed on sequential. It's also allowed on regular. Okay? Okay? It's allowed. But it's not allowed on linearizable. Because linearizable, it's global, okay? The whole thing, all the nodes together are one storage. So once you read a 5 anywhere, if you do another read later anywhere, it has to be 5 or a later write, okay? So you read 5 here on P3, later in the absolute time, you read 0, that cannot be in a linearizable system. So this is not satisfying linearizable. No single storage could behave in this way. If I read a 5, it's like these are separate threads. Separate threads. If I write 5, and then I read a 5 in one thread, and in another thread I read later, and I read 0, that's not possible, okay? These are kind of like threads, okay? If you want to, get the analogy. These are concurrent, but there is a single global time. So it's really a true single storage, and you can kind of think of it that each of these nodes is like a thread running on a laptop or a single machine. So that's linearizable, okay? You see how it works? Notice that sequential consistency is not stronger than regular. I mean, you can have regular be true and sequential be false, and regular be false and sequential be true. Because regular actually it looks at the overlap globally. So this is not allowed in regular, okay? Because the read here is happening after the end of the write. But it is allowed in sequential, because in sequential each one has its own local time, so we don't actually connect these two, P1 and P2. Sequential is that each node has its own local time only, okay? So this one is allowed in sequential, but not allowed in regular. So that's kind of weird, huh? But so you might think regular is always weaker, but it's not always weaker somehow, huh? It's just different. Okay. So those are the three levels, huh? And linearizable is the strongest. Okay. Before I give algorithms, I want to talk also about liveness. These conditions are actually safety conditions. Okay. They're safety conditions. I also need progress. I can only detect errors with them. Huh? This is disallowed, or this is not disallowed. But these do not guarantee progress. They can only detect errors. Okay? So these conditions are all safety. That means I also have to talk about liveness, but most of the talk today will be about safety, so I will have only one slide on liveness, just to introduce some liveness concepts. So liveness means the system makes progress. So when I do writes, the writes actually get done, okay? Okay. So there's three versions. So that you can define liveness in different ways also. The same way you have different versions of safety, 1, 2, 3, you also have different versions of liveness. Why do you have that? Why do people make life complicated? It's because sometimes the simplest versions are good enough and they're more efficient to implement. Okay, let me show you just the three here. The strongest one is called weight-free. This is very intuitive. Every correct node makes progress. So if I have 3 nodes, they're all making progress. But there's actually weaker versions. Sometimes you have this one. This is called lock-free or non-blocking. Okay, so I did not invent this terminology. At least one correct node makes progress. And the weakest one is called obstruction-free or solo termination. If a single node executes and it has no interference, so no other nodes are trying to use the same resources as it, then it makes progress. So this is weird, huh? So I have actually tried to make this more intuitive. So to make this more intuitive, I will connect this to sports, okay? Weight-free means that everybody needs to reach the end. When you run a marathon, everybody is competing against everybody. Every runner, correct node, should go forward, okay? That's reasonable, huh? Because they're all competing against each other. But sometimes you don't have that. Some systems are weaker than that. If you have a Tour de France, you have cycling teams. Actually, if you have a bunch of riders in a single team, only one of them has to be number 1, okay? The others are only there actually to help that one become number 1. At least one correct node should make progress. So this is more like a cycling tournament where each team, the teams are actually competing and not the individuals. So you can see that there are cases where this makes sense. You see this kind of a condition. Usually you have this one up. If you have threads, like fairness, this is more like a fairness condition. Every correct node make progress. This is a typical fairness. But you have also weaker versions. And the weakest version is called obstruction-free. This is a football game, soccer game, for Americans. Football game. Well, if I have the ball, I want to make a goal, and somebody is trying to stop me from making a goal. So there's interference. I'm being interfered with, okay? But if I have no interference, I will make the goal. I'm assuming that if nobody stops me, I will actually make a goal. If a single node executes without interference, it makes progress. But if the interference is strong, if the defense is very strong, the whole thing can go on and on and on, and no goals are being made. So this is called live lock. Live lock is when the system is running and running and running, but there's no progress. So the ball, they're passing the ball between each other, and the defense is defending very good, and it goes on and on and on. At the end, it's 0 points. Okay, happens, right? A lot even, huh? Boring game, right? Well, this is for a football game. This can happen. So the liveness condition on the football game is actually this. So if there's enough interference, nobody makes progress, and the score will be 0-0. Okay. Okay. There can be starvation. That means I can't even move. Or live locks means the goal is live locks means the system is doing something, but there's no progress. So the ball is being passed between two players, back and forth, back and forth, back and forth, forever, but never in the goal. Okay. So that's a live lock. Huh? So that's a weak condition, but it's the one you see in football games, okay? So you can see that these three conditions, in some cases, they actually make sense. Some systems actually have this kind of a... So if I have threads, for example, that are collaborating together, but only one thread has to reach some final state, then I'm here. Or if I have two parts of the system that are kind of competing with each other, then maybe no progress is made. So then I'm in the third case. So these are three liveness. Why do I give you these three liveness? To show you that liveness is not simpler than safety. Okay. So this gives you some important knowledge. So these are actually real systems, and algorithms are written for this. Okay, for these different ones. Okay, so let me go back now to algorithms. So that's reasonable, right? You get that? You get the sports analogies? Good enough? I think they're reasonable analogies. Okay, let's now go back to linearizable, the strongest one. So I'm going to focus on linearizable, okay? Sequentially consistent is a weaker version where the nodes can kind of be delayed with respect to each other. But the linearizable is really the one. When you want it, okay? So we can define it. Let me give a more precise definition of it, okay? So we have weight freedom. So if the node is correct, every read and write will eventually complete. That's reasonable. And we have linearization points. So this is how we simulate things being instantaneous. So the reads appear as if they were instantaneous, immediate, at all nodes, at some time in between the invocation and the response. You can actually say there's some time there, and you can assume it's like as if it was instantaneous at that time. And the whole thing is correct with respect to that. Okay? And it's the same for the writes. Between invocation and response, there's some point where it's as if it was instantaneous. It will not be, but the behavior, the values you read are as if would be the same if it would actually be like that. Okay? Okay? You also have to worry about failed operations, of course. Either they're completed at every node everywhere, or they never occurred. Okay? Exclusive or, that means one or the other, but not both. Okay? So that is the more precise definition. And I will show you some scenarios of this. Okay? You can actually make two definitions now. Let me make these two definitions. On the left here, this is the definition I just showed you. So we have reads that have invocation response. and writes also. So you can actually find points in time, and you can assume the read was instantaneous there, and the writes too, and the failed ops, they're either completed, so they're one of those, or they totally never happened. And so, but let's look at these two. They're instantaneous. Okay? So you can define it like this. But you can also define it like this, and this is it's interesting to compare. So here I have another definition. So notice the first part of this definition is exactly the same as regular register. So this is it's regular register plus something. Okay? That's another way to see linearizable. So the read returns the last value if it's not concurrent with another write or filled operation, or it returns the last or concurrent value. So this is the regular register. Notice the regular register only has a problem when there's an overlap. And here we add something. We add ordering. If a read precedes a read, if one read precedes another read, then the write will also precede another write. With this, we add ordering, and then it makes it linearizable. So basically, we make sure that the reads are read in the same order that they're written. Okay, that we never switch the orders around, and that's enough to make it linearizable. So those are two different definitions. But let me give you now some scenarios, okay, to show you, to get you some intuition. Okay? So here is a case. 3 nodes. I do a write 5 and a write 6. Here I do read 6, and here I do read 5. Is this atomic? So this is clearly a regular register, huh? It's regular, you can see that. Huh? But is it atomic? Is it linearizable? Is there a global single system image? Is it as if the writes were done, and the reads were done in one sequence like that? Is it like that? You tell me. Is this atomic? Is this atomic? Can I, if these are threads, running on a machine there, can I get this result? That's one way of saying it. Can I get this? If P1, P2, and P3 are threads running here, and they're sharing memory, okay? P3 thread writes and then writes. P2 thread reads 6, and P1 thread after that reads 5. Can you get that in a memory like that?
No.
No, huh? Of course not, because the memory is totally shared. So once you've read a 6, then globally you can never read a 5 anymore. Okay? The 6 is the value everywhere. Okay? So this is not atomic, huh? Okay? And in fact, you can actually deduce that with these linearization points. Assume that the write has to be somewhere in here, the actual instantaneous write. The write 6 has to be somewhere in here, anywhere. The read 6 has to be in here, and the read 5 has to be in here. Okay? It's clear that the write of 5 has to be before the read of 5, huh? Because the only way to read 5 is if you write it before. So we can say it like this. The instantaneous write time is before the instantaneous read time. Okay? Okay? Now, the read of 5 has to be before the write of 6. Because otherwise we could not read a 5. Once we write a 6, we cannot read 5 anymore. So the read 5 has to be before the write 6. That means the read 5 time, which is somewhere here, has to be before the write 6 time, which must be here somewhere, right? And the write 6 time has to be before read 6. That means the write 6 time has to be before the read 6 time has to be somewhere here, the write 6 is somewhere here, but the write 6 has to be before read 6. Because the only way to read 6 instantaneously is if you've written it. Okay? So from this we can deduce that the read time for 5 is before the read time for 6. Okay? But that's not true. The read time for 6 is before the read time for 5, so that's a contradiction. We cannot find linearization points. So that's just one way of showing formally that there's a problem here. Huh? You see, this read 6 means that the write point has to be here somewhere, huh? Because I have to write 6 before reading 6. Whereas the read of the 5 has to be after, it has to be before the write 6. That means the write 6 has to be somewhere here, but it can't be here and here both. Huh? So there's a contradiction. We cannot make it work with instantaneous things. You see? We're assuming that the reads and the writes are instantaneous, and we cannot make it work. But let me show you an example where it does work. Okay? So here's an example where it does work. We can find points and instantaneous points, and if the reads and writes happen exactly at that point, then we would get the same values. So that means it's as if the thing is completely single storage. Okay? So, for example, let me see. Here, for example, let me do like this. So, assume the write happens here. Some instantaneous point in between here. So the write happens there. Okay? At that point, instantaneously. The write 6 happens here, instantaneously. And the read 6 happens somewhere here, but maybe it's here, okay? So after, and the second read 6 happens also after. So you can see these, if the read and writes were done instantaneously at these points, we would get the same values. So this system is behaving as if the reads and writes happened instantaneously here at these points. You see that? So it's exactly behaving as if it were single storage. Of course, the read and write did not actually happen instantaneously in this distributed system, huh? But it's behaving, but our view of it is kind of vague, because all we know is that the write is somewhere in here. We actually don't know that this point, if there's a point here, huh? But our view of it is completely consistent with these single points. So if we actually would have been able to do it instantaneously at these points, we would get the same values. Yeah?
What if the write of 6 was after the read of 6?
What do you mean? The write of 6? You mean this point here?
Yes.
It cannot be. I mean, in order for us to get these values, this point has to be before the read. It has to be before. And all we have to know is that there exist such points. Huh? If we can find, I mean, if there's no space here, like in the previous slide, huh? These points just have to exist. Huh? We have to be able to find points that are instantaneous and that give us the correct reads and writes. Yeah?
With this method, we are not sure the algorithm is good. It may be good.
We can prove that the algorithm is good. The only thing we're not sure about is that these points, there is actually no precise time for these points. Huh? So these precise times, the system does not have these precise times. Huh? It's just a way of viewing the system's behavior. All we know is the purple, the blue things. That's all we know. We don't know any of this. It's just an interpretation.
We only have one view.
Yeah, all we see is this.
Maybe with another view, we could say, oh, with this view, we can deduce the algorithm is not good.
Well, if the points exist, then the algorithm is good. So if they exist, they exist. There's no other view. I mean, if you can find such points, such that the values are consistent with what you read, then the algorithm is good. That's the condition for the goodness. I'm not sure exactly how you're confused. See, these points don't actually exist. It's just a way of seeing that the algorithm is correct. The algorithm behaves as if these points were here. They could also be, they could be anywhere here. Huh? There's many possibilities, in fact. Huh? But there only has to be one existing possibility for the execution to be linearizable.
We don't have the actual time step.
No, we don't have
If
them.
we had-
They maybe not even exist.
If we had another view, another
What do you mean by another view?
another schema.
But
Of the
all
same
we
kind.
have is this. We know the beginning and the end, and we know what we were writing. All we have is the black lines and the blue operation. That's all we have. And then the question is, with these black lines and these blue operations, is the execution linearizable? That's the question. And the answer is, yes, it is, if there exist linearization points. So it's just a kind of verification procedure, in fact. Huh? So it behaves as if, yes, it was, in fact. It's just a way of showing that this actually is satisfying linearizability. There is not, these points actually don't exist. Huh? You can't assume something happening at this time. Huh? In fact, they could be any time here. Huh? Could be, but it just has to exist sometimes. That's all. So it's a mathematical condition for showing linearizability. Huh? Okay, so here's another one. So here's another one. Notice, so here I have 6, 6. Here I have another one. And let's try to find, now the idea is we try to find these linearization points. You can do it formally. In fact, they're like the inequalities. Huh? This is a formal set of equations, actually. You can see whether they exist. Okay, so do they exist here? So assume 5. Okay, then we have 5 here. So the right has to actually happen after this point, huh? And it has to happen before the read 6. You see that? So it could happen here, and the read could happen there. Okay? So this execution is also linearizable, because we can find points such that what we see is consistent with that. Okay? This is a little bit subtle, huh? So I know that there's other subtleties in this course, like partially synchronous system is also a subtle concept, but linearizability is also a subtle concept, how you define it for a distributed system. Huh? So I understand this is a subtle concept, but you have to try to understand what this means, huh? These linearization points. It's just a way of seeing whether your execution is actually consistent with being linearizable, okay? So it's as if it could have happened like this. If we would have had threads and the writes and the reads would have happened instantaneously on a single machine at these points, then we would have gotten the same values. You see that, how it's working? Okay. So this is the holy grail, okay, linearizable. Now let's try to make an algorithm for this, right? Okay. Okay, let me try to do that. Let's start with regular. Okay, let's try to build an algorithm a step up from regular. Okay. So here, for example, here we have regular execution, and we use majority fault. Okay. Okay. Now this one, majority. Okay. Majority. Okay. And like that. So this actually is a correct majority regular execution, okay? Let me, but it's not linearizable, okay? So this is how the majority algorithm works for regular, okay? You do a write to majority. You get acknowledgements from majority. Here you do a read, you get acknowledgements from majority. Here you do a read, you get acknowledgements from majority. And here a write, you get acknowledgements from majority, okay? So this is a correct regular execution. But it's not linear, okay? Problem is, we have something here, okay? You have a problem here. You see this 5 and 6. Oh. But maybe we can do something to improve it, okay? Okay? So there's actually, let's try to fix the algorithm. So how can we fix this algorithm so it works also for linear? So this one is not linear. It should be 6 actually, yeah? How can we fix it so that this will be a 6? Well, one way is if we read a 6, when we read a value, we also write the value at that time. Okay? So the idea is that when you read, okay, when you read, you make a write also. So when I read 6, I will also write a 6, okay? And that means reads that come after will be able to read the 6, okay? So let me see, what's the best way to explain this? So this read is too short, okay? I want this read to be longer. If we make this read longer, then we can do a write 5, a read 5, a write 6, and a read 6, a write 6 and a read 6. Okay? So in fact, what we're doing is the read inside of this read, let's also do a write. So it will take longer. Okay? This actually uses this condition here. Okay? If there's a read before another read, then the write has to be before another one. So the idea is that we force the read to do write, okay? A read internal to the algorithm, it makes a write. That means any read after that read will at least see what we have written. So it will see R, okay? Okay? So adding this to the algorithm fixes things, okay? Causality is used to enforce atomicity. So here we're using this ordering condition, huh? We're using this ordering condition. If a read precedes another read, then the write has to have been before. So we add a write. We add a write. Inside the read, we do a write. Okay? So the algorithm does the following. When we read, we make a write before responding. And then any reads that come after that will, of course, because there's been a write, they will see the thing that was written, okay? And that makes it linearizable, okay? Okay, there's an optimization, but let me not talk about that. Let me show that. So that is the idea of the algorithm, okay? So you see it's not so simple, huh? But we're not done yet now. So this is the one-writer algorithm. And let me now do one more final thing. Let me make the algorithm even work for multiple writers. So it goes in 2 steps, huh? We have regular register majority vote. Then we add the fact that the read does a write inside the read. But that's still only one writer. How do we do multiple writers? Well, each writer has a sequence number, okay? Each writer, any process now can be writer, and each writer will have its own sequence number, and the problem is they might be non-synchronized. Maybe one node is doing many more writes than another one, so the sequence number gets incremented more, okay? So they kind of get unsynchronized, so it doesn't work. The way to make it work is you have to coordinate the sequence numbers, okay? So here, for example, if I do write 5 and the sequence number is 30, then later on I do a write 6, but here the sequence number is still an old one, 28. So it's going to be ignored. It's old. I'm only looking at the last one. So the way to make it multiple writers is to make sure that every node knows the most recent sequence number, okay? Okay, so this one will not work. So the final algorithm we're going to say today, we're going to show today, this is doing a linearizable in the case of a majority vote. This is called read, impose, write, consult, majority. So in this algorithm, we do two things. So the read will write also, that's the first thing, read, impose. But when we do a write, we will first, before doing a write, we will ask all the other nodes, what is the most recent sequence number? We will consult the majority. We will read from majority to get the latest sequence number. Because we have to update, all the nodes have to increment the sequence numbers. So anyone who does a write has to have the latest sequence number. So before writing, you actually have to read from a majority to get the latest, the last sequence number, okay? And that's the final algorithm. So this gets complicated, you see, yeah? It gets complicated. There's two extra things with respect to the regular register, huh? So what if you do two concurrent writes with the same sequence number? You have to break the ties. So there's still a few little tweaks you have to do. Huh? If two nodes do concurrent writes and they have gotten the same sequence numbers, then somehow there has to be a global order between them. Okay? Well, actually, you have to do a tie break then. They have to decide. So the sequence number also contains process ID. So remember, this is a trick we saw a long time ago when we saw Lamport clocks, huh? So these two nodes have the same sequence number, they're doing writes, but they have to do the writes in the same order. So one of the process IDs will be higher than the other. So if they compare the process ID, then one of them will be ahead of the other, okay? And that's the final algorithm, okay? And then there's a few other things. So there's a few other tricks. If you receive a write with an old sequence number, you still have to send acknowledgements? Yes, you always have to send acknowledgements. You always have to send acknowledgements. Oh, this is getting complicated. I need more time to explain it. So there's some tricks you have to be careful about, okay? Maybe I don't explain that in detail here. Okay, so basically the idea is, just to summarize very quickly, that you have, I want an algorithm, I want to do a linearizable register, and I want to do an NN algorithm, and I want to do fail silent. So this one will work on the internet. So this is like the Holy Grail. So the solution for this, I start with, it's in 3 steps. One, start with a regular register algorithm, the majority vote algorithm, majority vote. But that's not good enough, because if I do a read and another read, I might read an old value. So I add something to this. I add in the read, I also do a write. That means when I do a read, the algorithm will also do a write. So if I do read after that, I will always see the new one. And finally, to make it an end version, I have to synchronize the sequence numbers. Because I can do the writes from n sites, from n nodes. So this is actually what's called a consult majority. So basically I read from majority to get the latest sequence number. To get latest sequence number. So that's basically the idea. So you have one and you add two things. And that gives us a linearizable and fails silent. So you can see this is not so simple, huh? So I have shown you this, but I have not actually shown you the actual code. The code is in the book. But I just want you to understand this. So I'm not going to actually ask you the details, okay? Forget that. But I want you to understand why we need these steps, okay? We start from regular. Why do you need to do this? Because if you do one read after the other, in linearizable, you have to read, the second one cannot read an old value. Okay, so you need to do something like this. And finally, if you have an n algorithm, the sequence numbers, you have to get the latest sequence number before you do a write. Okay? So that, you need these two extra steps. But then there's some details to make it work, of course, which I won't go into. Okay? So that's the final algorithm I give today. But I'm not giving you the code because we don't have time for that. But you have to understand the intuition of it. Huh? Why we need these different things and what it means to be linearizable. You have to understand that. Huh? Okay? So that's the final algorithm. Let me give just a summary now. Let me go take a step back now and talk about some different things. What we did today was we simulated shared memory and message passing. A distributed system is message passing. That's what it is. It sends message between nodes. And we showed how you can simulate a global shared memory. And in order to make it work, we just need majority of correct nodes, and it works. Okay? So we showed how to do that. What about the opposite? Now I want you to think just totally opposite. Can we simulate message passing in shared memory? Assume I give you a laptop like this, and I ask you to simulate a distributed system on that. What do you think? Can we do it? How would you do it? If I give you a shared memory, can you simulate message passing? So I'm asking now the opposite thing, huh? How do we do that? What do you think? Is that possible? Yeah?
We can use low-level primitives provided by operating systems, such as a pipe or whatever, to allow to process, to communicate, despite they are on the same computer and they share a file, not two files. Because
so we have to simulate nodes sending messages to each other. Yeah, so basically you have to kind of write a simulator. For example, you can store the channels between two nodes. There's actually messages in there. You can store them in memory, a register for every channel. Send messages by appending. So basically you have to implement the network in a sense. Every channel between every two nodes, A to B. You can receive messages. You either check whether there's a message in the channel, or the message in the channel, when it's there, it tells you which node is waiting for it. So that means that you know which node you have to execute whenever the message comes. So you basically implement message passing in shared memory. So maybe you've done like this already, huh? How do you implement? It's basically like multi-thread system, but adding message queues between the threads. So each thread is executing independently, but you also, they don't have shared memory. They are sending messages. So it's like implementing airline. How do you implement airline? You have to implement all of the concepts. Okay? Okay? So you can do that. So in some sense, shared memory and message passing are equivalent in expressiveness. Okay, you can say that you can implement one with the other. Not one of them is doing something more than the other. Okay. Okay. So let me just summarize now what we saw today. Give me a quick summary of what we saw. We want to do shared memory. Okay, that's the lecture for today, for read and write. It's basically consistency in the presence of failures and concurrency. We first defined regular register, which was weak. And we defined one N algorithm. So I started with a bogus algorithm that didn't work. I also showed you a centralized algorithm. But then the real algorithm that worked was called the read one, write all algorithm. So this one uses a perfect failure detector. So remember, the write has to wait for acknowledgments from all correct nodes. And then, in order to go to internet, we went to majority algorithm, or quorum. So this one is fail silent, so no failure detector. So this is what we did. Then we went to the next level. So this is the strong model, atomic or linearizable. I first showed you a single writer algorithm. So the idea is you do read impose. So the read also does a write. It imposes a write. And that guarantees that the reads are ordered. If the read imposes a write, then the next read will see the value from the previous read. Okay? Unless there's even more writes. But if there's no writes, it will guarantee see it. So you know the reads are ordered. So that works for single writer. If you want to do multiple writers, you have to add another thing. You have to make sure that the writer has the most recent sequence number. So before you do write, you have to get the highest sequence number. And again, you're going to consult majority. So you ask from the majority, and you know that one of them will know the highest sequence number, right? And then you have some small tricks. So if you have two concurrent writes, you have to do tie break, and there's some small things that you have to do, okay? And then that gives you a multiple writer atomic register, okay, which works in the case of no failure detector. So that gives us the strongest algorithm what we have on internet. You see, it's not so simple, huh? You agree it's maybe not simple, huh? So no, internet is not always simple, okay? But in practice though, the 1N model is very often enough. It's not often that you need to do NN, in fact. Most of the time when you write something, you know who's the writing one. And I gave you an example from the gaming world, but it's also in other applications. So it's actually rare that you need a true multiple writer, luckily, huh? And even in many cases, regular registers are enough, because you don't, if there's a few incoherencies, temporary incoherencies, when you have concurrent operations, in many cases it doesn't really matter. So for example, in Facebook, if occasionally there's a small problem in ordering and you read an old or an old tweet or an old reply once out of 1,000,000 times, then nobody will notice, right? So in practice, many people even use regular registers. Okay. So let me stop there for today. So with that, you see how to do distributed databases. Huh? So you have another pillar of the internet. With that, you can rebuild the internet. So let me stop there.